In this video, we'll go through the position error correction data reduction process for the GPS matrix inversion method, and we're going to do it in Python. Let's dive in.
3, 2, 1, top.
3, 2, 1, half, the Flight Test Engineering channel.
Okay, before we start our data reduction proper, I'd like to remind you that all of this code is available on our GitHub repo, github.com flight test engineering. And this one is available specifically in the PEC repo. If you go there, what you're going to see is that we have a few subdirectories here, and if you clone the full PEC repo, you're going to get the GPS and the tar flyby that we saw in the first videos as well. Moving along, so we first do our imports, numpy as np, which is our numerical package, matplotlib.pyplot as plt for our plotting, and I'm going to set the style to dark background because that matches what I have here. The constants and conversions are the same as well. We have meters to feet, feet to meter, knots to meters per second, and so forth. They're all standard, and we have also the International Standard Atmosphere, with our temperature at sea level, pressure at sea level, lapse rate, speed of sound at sea level, and so forth. We have seen this before as well. For our airplane, it's going to be the same, VMO at 350, VSTOW at 105, and these are the instrument errors that we're going to adopt on this data reduction. So for our airspeed instrument, we have 2 knots. For our altimeter, we have minus 20 feet, and for our temperature probe, we have minus 1 degree C. And we have the temperature recovery factor for our temperature as set to 1, so it's a perfect probe. And here we start with the flight test data. What we have here is we have an array, a NumPy array with 3 numbers. Because remember, for this method, we do 3 runs, each run on 1 heading, so these are the runs that we have. And these are the indicated airspeed. You can see it's fairly constant. The altitude is also constant, 6,000 feet. Then the outside temperature is 11 degrees C. And these are this is the data from the GPS that we got. So we got ground speed, 138, 133, and 120 knots. And this is our ground track, 7114 and 234. And the way we're building this is the classical way. We declare a NumPy array, and inside the array, we put a list with our numbers. Okay, and we start now from the anemometric side, so we're going to first correct our indicated values with whatever errors we had for our instruments. So we correct airspeed, we correct altitude and temperature as well, just by adding the deltas that we saw before, except for temperature that we are already transforming from Celsius to Kelvin, all right? So these are degrees Kelvin as well. We find QCIC over P0 ratio, which will be used for the Mach equation. We use our indicated airspeed to find QCIC over P0. And this is, again, just a feature of working with NumPy, which is great. We know that VIC is a vector of 3 numbers, and just by writing this equation, Python is going to understand that you have a vector here with 3 numbers, and you're going to get also a vector with 3 numbers. So it's going to apply the equation to each and every element of VIC without even running a for loop, which is great here. So you can see that we have 3 numbers there, each one corresponding to its own VIC value. We also calculate the pressure ratio, delta IC here, from the International Standard Atmosphere, also using our indicated altitude as a base. Same idea. Notice that we also we always use international units, SI, standard units. So that's why we first transform our altitude from feet to meter. Next, we find QCIC over PS, which is just a multiplication of QCIC over P0 times 1 over delta. And from QCIC over PS, we can find our indicated Mach number with this formula here. Notice also that I already printed the mean Mach number. And it's reasonable to start thinking about the mean because we have one of the basic assumptions for this method is that your indicated airspeed is going to be maintained constant throughout the 3 runs. Therefore, your indicated Mach number should be constant as well. And that's why we're going to use the mean. So from this mean indicated Mach number, we can calculate PT over PS, this pressure ratio. And to get the mean, what we did is we used this feature from NumPy, which is when you have a vector, you can have access to a bunch of metrics and functions that NumPy gives you. And one of them is the .mean method that actually calculates what's the mean value in your vector. Moving along, so now to find the indicated true airspeed, we need first to calculate what is our ambient temperature. So we're going to take our indicated temperature and divide by this factor to get our ambient temperature here. Notice that we're also using Mach number. And now we can calculate what is the temperature ratio, ambient temperature over sea level standard temperature, T0. And from this data, we can then calculate what is our indicated true airspeed from our indicated Mach number that we calculated before. Now we start the matrix inversion method, and from the GPS side, we remember that we have the ground speed is going to be our true airspeed plus the wind that we don't know. And as we saw in the previous video also, we can expand this term to have an indicated term plus the error, which we can isolate and write that this true airspeed is going to be our ground speed minus wind. The assumptions, just as a reminder as well, for this method is that the true airspeed error, delta VT, is going to be constant throughout all the 3 runs. And also, wind is going to be considered constant with no up and down drafts, and that the airspeed vector is parallel to the true airspeed error. So this vector is parallel to VT. This allows us to write that the errors in each run are the same, so they're equal. And because the vectors are parallel, we can write that these angles are the same, which allows us to write this equation in the pure form, no vector form, Vt equals Vti plus delta Vt. Remember our original equation where the true airspeed is ground speed minus wind. We then decompose this equation into the east and north components so that we have two sides of it. The first thing that we're going to do here in our Python script is create our ground speed east and north from our ground speed and track. NumPy is great here because you're going to apply the sine function to a vector, and that's going to be multiplied by another vector, giving you a vector without any for loops, any loops at all. So Python is smart enough to understand that this is a 1/3 vector, this is a 1/3 vector, and that you want to multiply element-wise each element and get a new vector from this. Okay, so now we have to assemble or form our matrices. We have, if you remember, we have first this matrix that we need to form. This is our solution vector, and this is our one of the matrices that also that we want to form. We called this A, this is going to be X, and this is going to be C in our previous video. And we're going to get the solution to X, we're going to invert A times C. Just a recap as well on the method is that since this matrix depends on the solution that we don't know, it depends on delta VT, depends on wind, what we're going to do is we're going to do this by iteration. So we first do a guess of what this vector is, we calculate this matrix, do its inverse, multiply by this vector, and get a solution, another tentative solution. We feed it back, calculate again, and keep iterating until the solution converges. Okay, so this is what we're going to start. We're going to start with the initial guess of our vector, all with zeros. So let's run this cell here to define our initial guess. And then here is our main loop. We start by defining what is the maximum iterations that we are going to allow. So we're going to set it to 100, which is plenty for this case. As you see, it converges pretty quickly. We set a variable here, which is a Boolean set initially to false that will mark when we have the loop converged. We also create a new vector called epsilon, which denotes the expected maximum error in our solution. And we're going to set it to 1 times 10 to the minus 9. And this variable here is going to count the iteration. So it's the iteration counter. Notice that it starts from 0 because Python is 0-based, unlike MATLAB, which is 1-based. The first matrix that we're going to calculate is the C matrix here, which is, if we go back, we can see that the C matrix is constant. It does not depend on our solution. So we can calculate this outside our loop, which is more efficient because you calculate only once, right? So how are we calculating it? Well, we're doing ground speed squared minus indicated through airspeed squared. Let's see how this works here in Python. So if I just run this code here, it's going to create a NumPy array. Let's see what we get. So we get a 1 by 3 array here. And that's why we need to put a transpose. And before we do that, we can check the shape here. It's a 1 by 3. And if we do the transpose, it's going to be a 3 by 1. And we can also check the shape here. It's going to be a 3 by 1, which is what we need for the matrix multiplication. Okay? And now we enter our while loop. So how do we read this? While our number of iterations is less than our maximum number of iterations, and we have not converged, then we're going to run this loop. Python uses the indentation to mark the blocks. So you see that this block here is all indented to the right, and Python understands that only this code is inside our while loop. So we start by assembling the matrices. We start by creating the matrix X with our solutions that we set to 0. So this is a simple one. And then the A matrix is going to be 2 times VTI plus delta VT, 2 times ground speed east minus V wind east, 2 times ground speed north minus wind speed north. So again, let's have a look here how we are assembling this matrix. You see that by running this, the airspeed, the VTI delta VT is all on one line, and that's not what we want. We want this to be a column. That's why we have to do a transpose to get the VTI plus delta VT all here in one column. So that's what's going on here. And now we're going to go and calculate our x prime by doing a matrix multiplication of the inverse of A times C. And here's a hint. You can use Shift-Tab to access the function help. So if, for instance, if I place my cursor here and hit Shift-Tab, the JupyterLab environment is going to give you what is the call signature for our NumPy function matmul, which is a matrix product of 2 arrays. And it's going to explain to you all of the inputs and outputs that you can get from this function. Okay? Same thing here with the linear algebra. I can, just for the kicks of it, put it here and then do Shift-Tab, and it's going to talk about the module NumPy linear algebra, linalg, that is based on the BLAS and LAPACK libraries that were written way back then in Fortran and C. And that's why this thing runs pretty fast, because underneath it's running very highly optimized code. Same thing with the inverse. Oh, I can show you one more thing, Shift-Tab here. And this is going to show you all of the functions present in the linear algebra module. So you have the multi-dot, you have Cholesky, eigenvectors, eigenvalues, And you can have the inverse and P inverse that we're going to use later on as well. Right, so let me just, oh, and if you put inverse here and shift tab, then you access the inverse function help. So it's going to give you the signature and again tell you how you what is okay to input, what is not okay. Okay, this is really useful when you're learning. So here we calculate x prime by multiplying the inverse of a times c. And then we calculate what is the accumulated error. So we calculate what is the error between our initial guess and our current solution. And then we square this and get the sum. This term here is going to always be positive. That's why we're squaring the deltas here. And then we print what is the iteration number that we are at and what is the error squared for this iteration. And then we check if our delta x, which is our sum of the squares of the errors, is less than or equal our epsilon, then we have converged. So we print out solution converge with so many iterations, and we print our solution here, delta vt, wind speed east and north. And then we set our flag to converge equals true so that we can get out of the loop on the next time we check up here, right? Converge is going to be true, and this is going to be rendered that the while has ended, and it's going to kick out of the loop. Then we feedback for our next solution. So remember that we have to form again our X matrix. And to do that, we use delta VT, V wind east and V wind north. On the first pass of this loop, we had set this to 0, but now we set it to the current solution. We increment the iteration counter and run through the loop again. And we do this until we converge. At the end here, outside of the indentation, outside of the loop, we check. If we did not converge, we have to tell the user that, hey, solution did not converge after so many iterations. Okay, so let's run this loop and see what we get. And we see that we converge in 4 iterations, which is pretty good. The solution is going to be delta VT minus 1.15 knots. The wind speed east is going to be around 8.2 knots, and the north component 7.3. Okay, now we calculate what's the wind speed by doing the square root of the sum of the squares of each component. And then we can calculate what's the wind direction with the arctangent function. We use arctangent 2 here in NumPy. But again, this gives you the wrong quadrant. So we have to add 2 pi and then do a mod 2 pi to get to the right quadrant. This is the remainder, right? Mod is the remainder. And this is the operator that we have in Python to do this operation. We are already transforming from degrees to radians here. So we see that the wind is coming roughly from 48 degrees. Now we can calculate what's the truth airspeed, the true airspeed, because we have our indicated and we have the error that we just calculated above, right? And instead of calculating 3 values here, we're going to again take the average of our indicated true airspeed and add that to our error to calculate what is the true airspeed in our system. We then calculate what's the ambient temperature from the true airspeed side. And with the same concept, we are going to use the average of our outside air temperature that we collected in our 3 test runs. And now we can calculate what's the temperature ratio, theta, by doing our ambient temperature over the standard temperature at sea level. And we can calculate what's our delta Mach by using our delta VT and then transforming that to the Mach domain using the theta and the speed of sound at sea level. Notice that we are transforming from knots to meters per second because our speed of sound is already in meters per second. And the truth Mach number is going to be our average of our indicated Mach plus our delta Mach that we just obtained. So from the truth Mach number, we can calculate the pressure ratio PT over PA. And finally, the position error ratio, delta PS over PS, is going to be 1 over PT over PS minus 1 over PT over PA, everything times PT over PS. So this is the goal, to get the delta PS over PS for the 3 runs that we had for this indicated airspeed, and then 1 altitude. And now we're going to go for the common part, where we take the results from 6 different test points, each test point with 3 runs, and then do our data expansion to go from our delta PS over PS to a delta HPC and delta VPC that allows us to check against the FAR 25 limits. So I'm going to run through the code. This portion was already shown on part 2 of the video, so I'm going to quickly run through the code here so that we can get to the graph.
If you want a refresher, you can rewatch that video. It's part 3 of this mini-series. So let's see where we get the graph here. Let's keep going.
There you go. That's the first graph. Let me zoom out. So we can see here, one more. We can see here that we have our delta HPC in feet against VIC in knots. As airspeed goes up, we see that the FAR envelope also expands. And we see that our results are borderline here on the FAR limits. This is the classic FAR 25 funnel plot for the altitude error. And if we keep running, we get the airspeed error as well. So again, we have VIC here on the x-axis and delta VPC this time on the y-axis. And this is a better story for our aircraft because it falls well within the limits of FAR 25. I hope you enjoyed this video, and in the next part of this mini-series, we'll see a completely different approach with the turn regression method. See you there!